All right, everybody that can see my screen. I think it is. Thank you very much, the Professor Shrubtap, for your nice introduction. My name is Duan Bei, as written here, and I'm an assistant professor of the Harriet White University. And today's topic is heat to chemical energy storage via dual redox flow cell system. Basically, we're gonna introduce the redox flow system or other type of the flow cell system for the heat to chemical energy conversion. Of course, I do both the theory and experiment at the same time in our lab, but today focus will be on theoretical analysis toward the Carnot limit. All right, let's get started. Let me start our presentation from the introduction to our school. Our university name is Harriet White University. It is a 200 years old historical university located in Edinburgh, and um, the student number is 29,000 students, and in department of the chemical engineering, we are ranked in third, and the physics ranked in the ninth. I'm working on the physical chemistry and the physics and other electrochemical energy storage, the research, and quite related, closely related to chemical engineering, and at the same time, the energy technologies, which is one of the important and the biggest research discipline in our university. We also have a campus in Dubai and Malaysia. Dubai campus is place. It's one of the best university by the Forbes Middle East the higher education, and already the 2019 as one of the best university. Let's move to our research lab. Our lab, I'm working on the photo and electrochemistry, but our lab is belongs to the research group called NESI, is Noble Energy System and Storage Integration. We have the four faculties, two in Edinburgh and two in Dubai. We particularly focus on the energy technology integration of two or three different energy conversion in the storage system to make overall energy efficiency high as possible. My research field is the photo and thermoelectrochemistry with a small scale. Most of them are laboratory scale, and I do, as I mentioned before, both the experimental and theoretical part. Some of our university faculty also do work on the larger scale integration modeling. For instance, the solar farm integration with the wind energy source. That some of them they work on the battery the management system as well, or some of them work in thermochemical the research. So basically, our NESI research group covers from both the lab scale to larger scale the study items. Among them, as I told you before, my research team to focus on the photo and the thermoelectrochemistry. Basically, they're using the redox flow battery and also the hydrogen electrolyzer for the hydrogen production. There are two big research pillars. The one is the photon to chemical, and the other one is the heat to chemical. Of course, the photon to chemical, two big items falls into this category. The first one is the solar water splitting, and the next one is the solar redox flow the battery. We will not focus on these two items for today's talk, but before moving to the serious part, let me introduce the representative that works for each item. So for the solar water splitting, I have record the longest photochemical hydrogen production in very highly concentrated acidic condition. We have shown the 91 days of hydrogen production using silicon for the photo to the hydrogen chemical conversion. And for the solar redox flow battery, using the same silicon structure, I have shown the solar to chemical conversion over 9.4% conversion efficiency. It was one of the highest conversion efficiency among the solar redox flow battery system using single cell. Of course, there is some very high efficient the solar redox flow battery, which has efficiency over 20%, but most of them they use um, tandem cell or triple junction cell, which is practically very harder to be commercialized. For the heat to chemical conversion, as you can see on the right side, the basically use the fluidized bed system. It is kind of can be the latent heat absorption or the phase changing material. The basic item, the fundamental mechanism of this the fluidized bed system is we the fluid through the this reaction, the bed, the hot and dry air from the heat source, and the material absorb that heat and expel the cold and wet air, and that energy in reverse reaction expelled in form of the hot and dry air when the energy stored energy is required to be used. But this type of fluidized bed system is basically designed for the heat to chemical and chemical to heat energy conversion. So once you store the energy in the form of the chemical, then that energy only can be exposed to the air in terms of the heat energy, not the electricity or other type of the energy. Other our research focus is the using the solar panel for providing the heat energy into this thermal bath, which is field of the phase change material. Shortly, it can be called as the PCM material. Together with the fluidized bath system in the previous slide, this is also one of our research focus. The sun amp is one of our the commercial industrial partner. We do not make ourselves the PCM material and the storage system, but together with the sun amp the company, that we are now testing this integrated system in our real testing field in our university. Let me move to the another type of the heat energy storage system, basically heat to chemical and chemical to electricity, so that we can reutilize that stored energy into form of the electricity. Now, what is the wasted energy? The wasted energy that can be basically the waste heat from the factory or household, which is not utilized in form of the work. Instead of that, just exposed to the air or just wasted in form of the other heat transfer. So the main purpose of this heat to chemical to electricity conversion and storage research is maximize the utilization of the waste heat. In terms of the waste heat, always the solar thermal energy, for example, the thermal energy that we observe through the building, the outer surface is also can fall into this category. There are the various type of waste heat energy which we can get from the industry. For example, at a high temperature region, waste heat from the steam or the cooling generation or the drying the process. Those are the waste heat falls into the high temperature heat energy. And for the low grade heat energy, though, we can categorize the ventilation system, the heat into this category, and the warm water heating system also falls into this category. Basically, only the 40% of heat energy is used in industry or household for heating up or for the useful electrical power. And rest of that, the 60%, is just a loss as the waste heat. If we divide them into the various temperature, the range, for the metal and the mineral industries, most of the waste heat is more than 1,000 degrees C. But mining, chemical the process, the paper and pulp, and the food industry, most of the waste heat from those industry, and also the plus household, they are very low grade heat energy. Unfortunately, up to now, there are the various technology which can be used for utilization of the high temperature energy, but not many for the low grade heat energy utilization. According to our the recent discussion from the UK Research the Council, heat energy storage is one of the biggest challenge for the net zero emission of the United Kingdom. So that is the main driving the momentum for this research. Um, in terms of technological readiness, we only have the good sources called the thermoelectric device. Basically, it is a combination of two different type of semiconductor, and by using the heat temperature gradient between these two, and they can convert the absorbed heat to electricity or absorb the low temperature condition and a high temperature condition by making these two temperature gradient, the heat electricity can be generated. But the disadvantage of this technology is their conversion efficiency at a low temperature region is really the poor. As you can see, only at the maximum 10%, or actually the pretty much most of these thermoelectrical device shows only 2 to 7%. And also cost effectiveness is quite awful. For the making the 1 watt, we need to spend almost 22 pound. In dollar, it can reach to the $30 almost. It is because the most of the semiconductor of the state of the art this thermoelectrical device made with the strontium or is the arsenide or telluride, which is not hard, is not easy to make in the form of the device. To solve this problem, in recent years, the many researchers they put the tremendous effort into development of this liquid-based thermal electrochemical devices. One of them is the thermal electrochemical cell. Basically, um, it's quite similar to the previous slides, the thermoelectric device. The one side is with a high temperature, and the other side is a cold, the region with a low temperature. And by doing that, the one can make the potential difference led by the temperature difference. And this make the potential difference at 2 and this is a driving force of this type of a thermoelectrochemical cell. As I noted here, the higher the temperature coefficient, the higher the cell voltage. The temperature coefficient here in this case is same to the Seebeck coefficient. So higher Seebeck coefficient, higher the potential the shift at sudden the range of the temperature gradient. The another type is the thermally regenerative ammonia-based battery. Basically this type of the battery, the driving force of the electricity generation is not the potential change by the temperature, but by changing the temperature, we can make the ammonia um, exposed to the space in form of the vapor at high temperature. while at low temperature it is dissolved into the electrolyte inversely. And by doing that, we can change the concentration at the between the two chambers, and this tempered concentration or reaction, um, the charging state change is a driving force of electricity generation in this type of the ammonia-based the battery. In for those two cases, the heat to electricity conversion is already 3 to 4%. Of course, it is not the commercially proven efficiency, but even in this, they are the lab scale study. But at low temperature, um, the gradient, for example, only 70 degrees C or less, they already show quite a good efficiency, which is already close to the maximum efficiency of semiconductor-based thermoelectric device. Another type is thermally regenerative electrochemical cycle, so shortly called the TREC. The main driving force is the cell voltage shift at two different temperature, depending on what the redox couple you choose. Of course, this can be changed, but if the one electrolyte has the increasing the potential at high temperature, while the other one shows a decreasing redox potential, then the overall cell voltage increase in this case. So by using the fundamental, if we charge at a low temperature and heating up and discharge at the high temperature condition, then we can make the electricity work between those two different the charging and discharging curve, and this is heat harnessing here. Basically, the working mechanism is almost the same to the previous slide's thermoelectrochemical cell, but different thing is in here the TREC case, overall cell works either high temperature or low temperature, and by using these two different the operating temperature condition, we make the heat stored into form of the electricity. Actually, this project is our ongoing project and recently funded by the UK Research Council. Now let's see the summarized efficiency chart for this type of electrochemical heat to electricity conversion systems. As you can see here in the left chart, one of the best conversion has been obtained by using the TREC, the battery, thermally regenerative electrochemical cycle battery, with kappa, two different the kappa the chemicals. One is a kappa metal, and the other one is a kappa hexacio the ferrate, as far as I remember. Hopefully, I pronounced it correctly. And here, the red color one is thermoelectrochemical cells, and the circular one is the redox ammonia, the battery. All these three types, it shows very obvious temperature dependency of the cell voltage. Here, the x-axis is a temperature difference between the high temperature case and the cold low temperature case. By having the high temperature gradient, it is obviously that we can make high conversion efficiency. But if we change the x-axis to the thermogalvanic coefficient, in other words, the Seebeck coefficient, it is not clear the trend in conversion efficiency. As I showed here, the most of them have lined in the thermogalvanic coefficient between 1 and 2. Even so, they have quite high well, some of them showed quite high quite conversion efficiency. In this case, the thermoelectrochemical cell, with the thermogalvanic coefficient. They have a very high Zivec coefficient, but still the conversion efficiency only between the 1 and 3. Well, shortly, there is a strong temperature dependency, but not clear trend in temperature coefficient. It is basically, it is because all these cases I have shown in the previous chart is a very low technological readiness level, which is a lab scale, and uh, engineering spec, they are all not mature and not well designed. Um, from now on, I will discuss about these things for discuss the what we need to spend more time for the making higher efficiency system. The first one is the architectural aspect. We already know that the how the TEC and the TLEC and the TLAB the works in the previous slides, but unfortunately there are huge thermal loss by the heat diffusion. For example, in the TEC system, both the two and the cold and the high temperature, and there is a huge heat transfer, and that drags down the practical temperature gradient between these two ends. And also TLEC and the TLAB system, even they charge at the low temperature and discharge at the high temperature. But unfortunately, between these two transition, we also can have a huge loss in between, heat loss in between. And the most important thing is, unfortunately, we can only do charging or discharging one by one, not at the same time. That is the quite big disadvantage of this kind of electrochemical heat to electricity conversion system. And per component aspect, all these studies in previous slide, they have a focus on the temperature coefficient design to make the high Zivec coefficients or thermogalvanic coefficient for their redox couples. And temperature gradient, that's fine. And also regeneration efficiency. They also spend some time to make the high efficiency of the heat exchange. But unfortunately, most of them has only the 50% or less heat regeneration efficiency because they have used a very poor heat exchanger. None of them, unfortunately, have discussed about the system resistance, for example, ohmic resistance or concentration resistance, and the flow rate condition. Unfortunately, there are not many studies that have looked into those two things in depth. So, um, from now on, we will discuss about the dual flow cell system and to discuss this temperature coefficient and the system resistance and the flow rate also and heat regeneration efficiencies, which has not well studied in the previous study. The reason why we have suggested this dual redox flow cell system is unlike the previous TEC and the TLEC system, by using this dual redox flow cell system, we can charge and discharge the both at the same time. It is because while the hot cell observed the heat from the outer source and operating the redox reaction, and the other cell in the cold side it works for discharging the electrolyte which has been charged at the high temperature. So unlike this typical single cell system, the cell voltage and state of charge behavior, if we use this type of the system, then we can keep the cell voltage always the same. If the both charging and discharging reaction rate are the same. The main drive focus of main application of this kind of system is can be the household. For example, in the UK or in some area of the Middle Eastern Asian countries, they has many of the thermal collector, photothermal, um, the heating system at the household. If we utilize this system, then we can provide the heated electrolyte using a thermal collector, and that heated electrolyte will provide um, the high temperature electrolyte condition for the hot cell, and by using the heat exchanger in between, we can provide the heating or hot water for the household. And by operating the cold cell at the other end, we can supply the electricity to the home appliance. This is the basic idea for developing this kind of system. Also, this system can be used for the other industrial application. For example, the factory, by absorbing the waste heat from their chimney, or data center, instead of the cooling by ventilating system, we can just make the flow of the cold electrolyte to heat it up, the electrolyte, and this heated up the electrolyte can be used at the hot cell for the making the electricity generation. All right, now let's talk about the um, what is their potential, what is the charging discharging performance of this type of two-cell system. I would like to note once again that most of our work today there will be theoretically based work, and there will be the many equations and derivation process, but you don't need to um, uh, give too much attention on this process. The important thing is how we derive the equations. The important message is the physical, the meaning hidden behind. All right, so let's start. Um, the conversion efficiency of this kind of temperature gradient heat to electricity conversion system is defined by using this equation. The power output over the heat applied to the hot side, right? So if we put the power output equation and here apply the heat equation, then we will get the maximum efficiency equation with here the ZT, which is called the figure of merit of a thermoelectric system. Well, actually, this type of figure of merit and conversion efficiency equations is already has been suggested by the Soviet Union time scientist Iofil. It's quite a long time ago, more than 60 or 70 years ago. But unfortunately, using this figure of merit and this type of equation, it is not valid anymore for this type of liquid type electrochemical system. So what we have done for our recent work together with Professor Anders Van Tien from the Aarhus University, Denmark, is we have applied the empirical thermal conductance, which has here the flow factor and heat exchange efficiency of the heat exchanger into them. By applying these new the parameters, we could have the new type of the efficiency calculation equation, which is suitable for this type of the electrochemical, the flow cell type heat to electricity conversion system. We go back to the extended version of conversion efficiency equation. As you can see, we also have resistance ratio factor together with flow factor and heat exchanger efficiency, and also the Seebeck coefficient, right? and also the resistance factor. Here, RL stands for the external load. This can be membrane resistance, mass transport ion resistance, and the R is R is internal resistance, and RL here is the external load, which is work can be done by this operating this system. So by using this analytic the model, we can um, investigate the impact of all these important working parameters for this type flow cell type, the electrochemical heat to electricity energy conversion system. This is the result, and shortly, by using the system with the CV equations of the 5 millivolt per Kelvin and hot and cold area temperature gradient is 80 degrees C, we can reach almost at the 19% of a conversion efficiency, as you can see here. Under this assumption, the kernel limit is almost 23%, and there are very small gap between 3 or the 4 efficiency. Of course, this is the ideal case, but we for the first time suggested what is the theoretical limit considering the practical working condition of this type of a flow cell. So important message here, if we use the poor heat exchanger, the HE stands for the heat exchanger, poor heat exchanger system, then we only can have between the 2 to 3%. And the other important and also interesting feature is depending on the flow rate factor, our achievable the maximum efficiency varies significantly. So if a flow rate factor, shortly flow factor increase, then of course the obtainable conversion efficiency significantly drops. Then let's see what factors that we can change for making this system with a low flow factor. According to the well-known equation for the flow rate the factor here, so Q. I don't want to spend much time your time for explaining this equation, but this gamma stands for the flow rate. Most of the battery flow cell battery has a 3 to 10 the flow rate factor. One of the approach is the increasing the concentrate of the electrolyte, but at the same time what we can do is we can choose the redox reaction with high electron number. For example, in the vanadium case, they are the one electron reactions, as you can see here. There are 2 electron the reactions. For example, brom, which is a quite hot topic in these days in redox flow battery field, and iodine and zinc. In recent days, we have very huge interest in those 2 electrolyte because those 2 redox couples can their solubility is very high. 8 electron the reaction. We also can find from the literature is a hydrogen sulfonated reaction, but unfortunately, this produce H2S, which is quite toxic. So I don't think that this can be utilized for this type of the system. Let's talk about the solubility. As I told you before, the for making the low flow rate factor, we can increase the concentration of the electrolyte so that we can have the minimum flow rate as minimum as possible. Unfortunately, the most of usable and also already studied redox couples in this field, they are all in between the solubility in between the 1 and 2 mole per liter in water base. But as you can see here, some of them, for example, iodine, particularly the potassium iodine, which is very easy to achieve from the market, right? And also sodium iodide here. They also have very good solubility, which is almost closer to the 10 mole per liter. If we can use that, then we can minimize the flow rate factor low as possible, hopefully below 3 and 2. Now let's talk about the Seebeck coefficients. In other words, the thermogalvanic coefficient. No matter what, the how this cell voltage changes at different temperature, it can be large or it can be small. Important thing is the overall absolute value of thermogalvanic coefficient should be maximum as possible to make this kind of a system the very highly efficient system. So um, let's talk about the ferrocyanide with the copper, uh, the triamine system. In these two combination, the good thing is they have the very huge difference between the high temperature and the low temperature in terms of the cell voltage with in terms of charging capacity. But disadvantages is they only have a cell voltage of 0.3 volt. So if we use this system, then we can have high cell voltage difference at the different temperature condition, but overall conversion, overall system power will be quite low. How about the vanadium case? Using conventional vanadium redox system, we can have the very narrow gap between the cold temperature and the high temperature condition. But good thing is that their cell voltage is pretty much high enough. So our goal is finding something in between, having a very high cell voltage and at the same time very high the Seebeck coefficient, thermogalvanic coefficient number. Let's see this chart on the right side. If we have a high number of Seebeck coefficient or the thermogalvanic coefficient, both the conversion efficiency, this is the efficiency at the maximum power point, conversion efficiency and the power density can be the maximum as possible. So that is why we have highlight why we have high the Seebeck coefficient, the number for the chemical system. One of our suggestion, according to our theoretical study, is this the nickel, the hexacyl cyanotefari, right, and the zinc metal system. By using these two combination, we can have cell voltage of 1.12 and theoretical the thermogalvanic coefficient is 1.1. And by using that, theoretically, we can have converted the 12% of the heat energy into chemical and electricity conversion. Actually, this already has been tested by one of the U.S. University, but unfortunately, their efficiency only was 2.4. The main problem of this study was the very poorly designed the insulation, and most of the heat just lost during these the two different temperature operating conditions. Let's move to the heat exchanger. The importance of heat exchanger is highlighted in this right side. You can see here at the high temperature gradient condition, no matter what, how flow rate was, if the heat exchanger efficiency is pretty much high, then we can have a 10 to 12%. But if we have the poor efficiency of a heat exchanger, as you can see here, depending on the flow rate factor, the huge drop in the conversion efficiency. These are the figures highlight that it is important to have high temperature gradient and at the same time, good efficiency of the heat exchanger. Now let's see this chart here. Here, these the solid black curve is the maximum efficiency with the heat exchanger. If heat exchanger is 90%, here the solid line, and dotted line is for the 80%. There's a huge drop. It is quite obvious, but here you can see that if we compare that conversion efficiency with the kernel efficiency, here you can see that at high temperature gradient, this relative heat conversion efficiency compared to the kernel efficiency decrease. But the power, this red curve, increase a lot. So engineers always need to consider the efficiency and the power balance in the between. Let's see what heat exchanger type we can use. Probably the most of studies in your lab as well always use this type of the thermoelectric device for the heat exchanger, or this type of glass tube type condenser like the heat exchanger. Unfortunately, those two are the very poorly can convert the heat to convert the heat with low heat efficiency, while this type of commercial style, the plate like the heat exchanger can show the over 90%. This is one of the case study. Actually, this case study using two different red fluor cell, it has been published quite recently by one of my previous colleague at the TU Delft. Unfortunately, our paper theoretical study has been published just several months before my colleague in TU Delft, Professor Bermas, published their experimental paper, unfortunately. But anyway, let's talk about this case study. They used the hot flow cell and the cold flow cell, exactly same to our theoretical model. And they used the ferrocyanide system and iodine. It is also same to our theoretical study. Actually, I can say this experimental study exactly duplication of our theoretical study in experiment. But unfortunately, their conversion efficiency is only 0.004%. Quite interesting point is if the heat exchanger efficiency is ideal, they could reach 5.2%. So this experimental study highlight how important to have this good heat exchanger system. Overall, the poor heat exchanger and the poor thermal isolation of the system was the bottleneck of this case study. As you can see here on the top right side, their heat exchanger system was a glass heat exchanger without any heat isolation of this tube and outer side of the glass tube. So naturally, they could have huge amount of heat just wasted to heat up the air outside. And we at Harvard University, we are working on not duplicate but just reverse engineering this case study for improving conversion efficiency as maximum as possible. Now is the last chapter. Let's talk about how we can observe, how we can obtain this heat for making the hot cell work at high temperature. Of course, we can apply the heat source from the external electricity, but if so, then it cannot be, say, this green energy storage. What our first approach is, let's use the solar energy, solar thermal energy more precisely for heating up our electrolyte. We have made ourselves, as you can see here in the top right, the heat solar thermal collector for the lab scale, just 5 to 5 square centimeter, in total 25 square centimeter. But unfortunately, thermal efficiency, conversion efficiency is only at maximum 40 to 20%. But we expect that we can reach up above the 70% if we scale up this heat solar thermal collector. Together with the Soltropy, one of our Scottish partner, we also work together for the making highly efficient heat collector. Particularly, our focus is on this heat transferring system between solar collector and the water pipe. This work is basically has done by our NESI research group leader, the Professor Tiger Donovan, together with his PhD student and together with me. And Soltropy invests a lot of money for developing this system. And this is also installed in our Harvard University and still under testing. And other example is kind of the budget version of our heat solar collector. This is the coil type heat collector. You can just unbox and assemble yourself and connect it the one end to the electrochemical system or pumping system. You can get the high temperature water-based electrolyte above the 70 degrees C at the peak time of the summer. Other item is a photovoltaic thermal collector, shortly called the PVT. By using that, we can collect, get this photon to electricity energy conversion, and also at the same time the thermal collector, because underneath of this PV module there is a water pipe, and this water absorbs the exact heat of the photovoltaic cell to keep the photovoltaic cell work at their best condition, and this absorbed heat transferred through this water and by end pipe by the pump to heat up this household the water heating system. This is the image of our PVT panel installed in our testing bed. Here in this hut behind, we are now testing the PCM material for storing this heat to chemical form. Other application is if we can utilize the absorbed heat, no matter what, whether it is absorbed from the sun or from the side of the building inside, whatever. If we can operate this electrolyzer at high temperature, then we can promote the reaction kinetics so that we can get the hydrogen at lower the overall potential. This is quite recently funded by our UK Royal Society, and it is just started from October. Actually, the TLEC system and this photothermal water electrolyzer system has quite a similar systematic illustration. That means we can utilize using the same heat collector system and same pumping system, but just using different stack cell, we can test both redox flow cell system and electrolyzer. At the moment, we are testing the very small scale, for example, 25 square centimeter. This is the photo of our solar redox flow battery cell system. And here, this metallic one is a redox flow battery system with the cell area is a 25 square centimeter. But our goal is increasing the size of this active area. For example, this one using this larger scale solar simulator, we can test at a larger scale solar thermal energy redox flow cells converting system. At the same time, the photo electrochemicals redox flow cell system. And further, our goal is installing in our testing field using larger than the 100 square centimeter cell system. Let me summarize our today's talk. First, we have reviewed the temperature gradient system for the flow cell application, TEC, TLEC, and TLAV, and we also discussed the disadvantage of those systems. And to avoid this disadvantage, I have introduced a dual cell redox flow cell system, which work at the one side at high temperature and the other side at cold temperature. By using that, we could maximize the heat to chemical electricity conversion efficiency over 19%, close to the Carnot efficiency. And we highlighted how important the Seebeck coefficient, heat exchanger, and the flow rate factor, which are three important practical operating factor of this flow cell system, which is overlooked in previous studies. The future focus will be design of a new electrolyte system for having the high Seebeck coefficients. We are now actively working on that. But important thing is this should be quite stable at high cell voltage condition. And also upscaling is also one of our future goal. And we also now focusing on the other application of high temperature technology for electrolyzer system. I would like to thank our member at our electrochemical energy conversion storage lab, so Ms. Olaya and Whiteley, and also Tiger Donovan from our thermal lab, which provided our Edinburgh testing site with the thermal and temperature monitoring system, and Professor Bentian from the Aarhus University, and also Adelio Mendes from the University of the Porto. And I would like to thank our funder, the UKRI, the EPSRC, and the Royal Society, and the Rennie Show for their supply of their measurement system. And also I would like to promote our hiring the postdoc position in our lab. If you have an interest, then please go to the link and please apply. And also, thank you very much for your attention. All right, so this is it for today. And if you have any question, then please.
Yes, please, if you have any question. Yeah, we have questions from the.
Oh, there is a question in the chat box. All right.
Yes, the chat box.
Yes, I'm interested in your working, tackling, collecting waste heat, transferring it to useful application. Curious with such system, what happens if one of the input and output stops? No sun, no electricity. That is a very good point. Well, it is not only applied to this type of a system, but also can be applied to other renewable energy system, for example, the wind energy or tidal energy. In short, if we do not have sun or low temperature condition, for example, Scotland, actually I'm living in Edinburgh, and outside the temperature is in the morning 3 to 4 degrees C, which Thailand cannot imagine, right? But anyway, if we do not have a sun, then there will be no supply of the heating source, so that we can not convert we cannot generate the electricity using that sun. That is a reason why we are now we will focus in the future for applying our system for the industrial application, for example, factory or data center or other type of fabrication manufacturing the facility where we can have always waste heat. It is because in case of the factory or data center, they should operate 24 hours, 7 days overall year. Then we can get the heat source, which is always quite stable unlike the solar cell system, solar energy system. All right, the next question is, how does the heat exchanger gives a rise to voltage? That is a very good question. One, let me review this heat to chemical energy conversion system, so called thermoelectrical system, cell system, and thermally regenerative um, the electrochemical cycle. It's better to share the screen again. I will go back to the slide where we have discussed about this item. Yes, these slides can be a good example. Here, you can see that if the one cell at a cold condition has a low voltage, and here at high temperature, the other cell will have a higher voltage. And this voltage difference between two cells is the driving force of the electricity. It is because always the electricity goes from the high cell voltage to low cell voltage condition. So this is the driving force of this dual cell type system. Okay, so if here high cell voltage at high temperature and low cell voltage at low temperature, then we can have the voltage, the gap between those two. That is a driving force of this type of dual cell system. But if we go to this TEC system, which is pretty much the well known system in this field, here they use just one single redox couple, but at high temperature, for example, this the ferrocyanide case, their redox potential pretty much high, while at low temperature, their redox potential pretty much low. And redox potential at this point and voltage at this end, they will have redox potential gap arbitrarily this amount. And this is a driving force of electricity generation. Hope this is pretty much clear for you. Right? Okay, then now the other question is, oh, what is a Seebeck coefficient? Yeah, Seebeck coefficient, in other words, is a thermogalvanic coefficient. So that represents higher thermogalvanic coefficient, higher the redox potential or cell voltage shift. What is the advantage of the charging and discharging at the same time? Well, this is a very good point. It is because if you have but only one single cell system, then you can charge that battery at high temperature. For example, at peak time of the day, for example, 12 to the 7 p.m., you can charge the battery, but you can discharge, utilize that stored energy at nighttime only. But if we have a two cell system operate at the same time, one for the charging and one for the discharging, then we can utilize stored energy just right away. So no matter what you use your system at day or night, one cell can charge and one cell discharge, so you can utilize your system any time of the day. That is the advantage of this system. All right, so informative talk. Thank you very much. Thank you very much for your comment. And the question is, is it possible that hot and cold cell system work independently for a single cell system by connecting two salt bridge? Yeah, that is possible. That is basically that is a fundamental of a thermoelectrochemical cell, which works at two different condition, but using only single cell. One cell exposed to the cold side and the other electrode exposed to the hot side. And one can make the cell voltage difference by using these two different temperature electrode. But the disadvantage of this system is in between, even though you have membrane, there will be huge heat diffusion in between. That limit the practical conversion efficiency of this type of system. And the other thing is, however, the question, what is the unique feature of the dual cell heat engine? Dual cell heat engine advantage, the first is we can charge and discharge at the same time. The second, we don't need to care much about the operating cell voltage of the each cell. It is because the power produced by this dual cell system defined by cell voltage, operating cell voltage at high temperature and a low temperature cell. So even though one cell, the operating cell voltage is only 0.2 or 0.4, it doesn't matter actually. Only important thing is how huge the gap between the cell voltage between the hot cell and the cold cell. But if we use only one single cell system, it is very important to have one redox couple and the other redox couple, for example, cathode and anode system. Those two ends should have huge difference in the redox potential position. All right, now that will a short circuit in the system occurs if a charging and discharging can provide at the same time. Well, I would say yes, but compared to the thermoelectrical cell or thermoelectrical semiconductor-based device, there is a very low possibility of the short circuit. It's because each cell has the water flow cells system, and in between there is the membrane. Normally, short circuit between the two electrode in this type of energy converting system happen when there is the physical contact between the two electrodes. But in our electrochemical system, there is always the physical distance is kept during the operation. So I would say there is a very low possibility of the short circuit between the electrode. But between the two operating cell in dual system, I would say, well, I'm not sure yet because we are now working on system building at this moment. I would say so. Well, not sure. Thank you very much for your comment. All right, then since it involves heat, can it be made into portable cell? Well, not the portable, but I would say we can utilize the system for mobility. Actually, one of the experimental dual cell case I have shown in the later part of our talk, it has been designed for applying the electrical car. Their motivation is installing two dual cell system into car for operating the car so functional like the ordinary lithium-ion cell system. But I have a quite skeptical viewpoint of that because anyway, we need to operate the pumping system for circulating the electrolyte that is quite heavy. So my suggestion is we surely can apply our electrochemical fuel cell system, even no matter what, it is a single system or dual cell system for the shipping industry. For example, large scale the ship or large scale offshore structure, for example, lighthouse or um, stationary or low-speed mobility system. All right, so I think I covered pretty much all questions here. Thank you very much for your attention.
Yes, thank you very much. Thank you again, Professor Bay. And well, thanks our sponsor, the Program Management Unit for Human Resource Institutional Development, Research and Innovation. Well, thank you again. So have a
Thank you
good
very
day.
much, Professor
Bye-bye.
Sultan. Thank you. Bye.
Bye.
Have a nice day. Bye.